Okay. We had talked about how strings are stored, that we have an array of characters, and within the declared size of the array there has to be the string end symbol, the \0. That was the requirement for being a C string. Now, this is basically just a convention. I mean, you have this array of characters, and the convention for it being a C string is that the \0 occurs within the declared size. Obviously, if you have a function that operates on individual characters, it is easy to lose that \0 by overriding it accidentally. You made a mistake in your program, and you accidentally override the \0, and then what you have is no longer a valid C string because it's not null terminated within the declared size. The functions that operate on strings, they all rely on this convention that the \0 indicates here is the end of the string. So any such function, when it processes the characters of a string, it will go character by character until it reaches a \0. Now what happens if you accidentally override the \0? What happens if you accidentally override the \0? Say you have this in memory. Say you have in memory an H, an E, an L, another L, and an O, followed by \0. And say you have declared the size of the array that holds this to have a size of 6. So this is your entire array. This is what you declared. There's other data behind it, other data after it. So if you write a program that accidentally overrides this, let's say with an exclamation mark, then you no longer have the \0 within the declared size. Now, functions that process this, maybe in order to output it or in order to attach another string to the end of it, or whatever other purpose you want to use this for, those functions will all rely on the fact that there is a \0 occurring within the declared size of this array, which is not the case anymore. So what will those functions do? Well, let's say a function that just outputs the string. If you just insert it into the output, it will start with the H. That's not a \0, so it goes to the output. It will continue with the E and the L and the L and the O and the exclamation mark, and then that's still not a \0, so it will continue with the next character, the next character, the next character, and so on. So it's completely undefined what will happen. It could be that these memory locations after the array are not part of the memory that was assigned to your program, in which case you get a runtime error, segmentation violation. It could be that there is data here for your program. It's actually part of the memory that has been assigned to your program, but that data was put there for a completely different purpose. Let's say it was put there to represent the integer, whatever, let's say the integer 15. The integer 15 internally is represented, well, in that case that wouldn't be a problem. Okay, let's take a bigger number. Let's take, maybe that's not a good example. What I'm after is that it's not a good example because the 15 happens to have some zeros here possibly, which would then act as \0s, which would basically kind of defeat my example. So if you have a very large number that has something non-zero here, something non-zero here, something non-zero here, and something non-zero here, then as a number that would be whatever, maybe 13 billion and some, no, not 13 billion, maybe 1.3 billion and some, let's say. But if you interpret the individual bytes that make up this number as characters, then they come out as total gibberish, as some graphical symbols or whatever. Normally not something legible. Definitely not something that makes any sense. Yeah, so whatever happens is more or less a matter of chance. How was the memory allocated? How did the compiler decide to allocate the space for the different variables? Is this part here actually part of the memory that's allocated for your program or not? Yeah. To summarize, it's undefined what happens. The next slide, that's the number 11, slide 11, suggests that there's a safer way of doing that. If you know the declared size of the array, then you can put kind of like a shield in place, a guard in place. And that guard is that you don't just look for the \0. You also check whether the index is less than the declared size. And if the index becomes equal to the declared size, then you stop processing. That doesn't really solve the problem, because the problem is that somehow, I mean, you're supposed to have a C string there. So there is supposed to be a \0 there. So the problem is where you lost that \0. What you would do with this suggestion that's here on slide 11 is that you're limiting the damage that will be done, right? You don't solve the problem, just limiting the damage. The problem is still there because for some reason your program overwrote the \0 that was supposed to mark the end of the string. Yeah? So that's where the problem is. That's what you should look for. But to be on the safe side and to limit the amount of damage that can be done, you can put this and the index is less than size in there, guarding against processing something here that wasn't meant to be used as a string. Obviously, that's a solution only if you have access to the declared size of that array. That's not always the case. Sometimes you don't have that knowledge. Sometimes the function doesn't get that size passed in, and so that you don't have that option. Then you must rely on the \0 being there. Okay, slide 12. We saw that you can initialize a C string when you declare it, like we did with that C string message having a size of 20, and we initialized it to hello. That's possible, and that's basically the only real convenience that C string offer. You can initialize a C string to a literal string constant, but you cannot use assignment, at least not the way you're used to. So you cannot use the assignment operation to then say message is equal to whatever, goodbye. That, where's my red? That is a syntax error. That does not work. Yeah. So assignment using the assignment operator does not work with C strings. And because it doesn't, well, you have to use something else. And what you have to use is you have to use a function that is called strcpy. short for string copy. And because it is supposed to mimic the assignment, you would put the target as the first argument and the source as the second one. So this assigns goodbye to message. Yeah, so it takes the characters that are in the string that is passed as the second argument, and it copies character by character over to the array that is passed as the first argument. strcpy. And it does copy the \0 at the end, and that's when it stops. Now, important, it is your responsibility as a programmer to ensure that message has sufficient space to hold all these characters. If message were declared to have only 6 characters and you would use that, the compiler would do exactly what you tell it to do. It would start at the array message, and it would copy the G, the O, the D, the B, the Y, the E, and the exclamation mark, and the \0 to those positions, right? Overwriting whatever follows that array. Yeah? Again, it's undefined what happens if your program tries to access these positions, because they might not be part of the memory that was assigned to your program. Okay, so it's your responsibility to ensure that there is enough space. And in order to use the function strcpy, you have to include cstring. You have to do an include cstring, and that allows you to use the strcpy function, and then of course you have to declare the target array. And on slide 14 we have again this problem that I just mentioned. It does not check the declared size, it just copies character by character until in the source string there is a \0. Okay, now the next slide, slide 15, suggests a solution for strcpy. That suggested solution is called strncpy. And strncpy has an additional parameter. Let me do that by wiping strncpy, and it has an additional character, additional parameter. So in the column we have an additional argument, let's say 20. Now this is, actually we should say 19. What this function does, strncpy, it copies again from the second argument, character by character, to the first argument until it either reaches the \0 or it has copied this many characters, whichever occurs first. So either we encounter a \0 within those characters somewhere, then it stops, or we have copied this many characters and then it stops. Now the slide says that this is a solution for the problem that we're having. Not really. strncpy is still problematic. It still has pretty much the same problem. There is an operating system called OpenBSD, and that operating system has one goal that goal is to provide a secure platform for routers, for servers, and so on. But the main goal is to have a correct, secure platform. What they did, I mean the team behind OpenBSD, it's an open source community. What that community did, they did a complete audit of the source code, checking every line, asking themselves, having a list of potential problems, of well-known problems, asking themselves, is there a problem, a security problem with this line of source code? And they found that very many uses of strcpy and strncpy were done incorrectly. In order to understand why this happens so easily, you have to know what exactly strncpy does. Well, if the \0 occurs within those 19 that I have here, within those 19 characters, then the result in message will be null terminated. It will have the \0 copied. But if the string here in the second argument is longer, hello and welcome everybody, let's say, yeah, that should be more than 19 characters. If that string is longer, then the copying stops after 19 characters, but the string at the target is not null terminated. It's not automatically null terminated. So the programmer has to remember to always, for safety, to always put a \0 in that last position of the array. Yeah, and the programmer has to remember that. And the thing is, imagine this number is a little larger, let's say it's 1,000, yeah? And you can work with longer buffers, and you come up with some test cases, and your test cases are 15 characters long, and they're 20 characters long, and they're maybe 500 characters long. Well, you only really trigger the problem if you get to the maximum length that's possible, to the declared size. So if you declared it to have length 1,000, then you only really get to the problem when you have a test case where you're copying from a source that has more than 1,000 or more characters. Only then do you see the problem. Or no, you don't necessarily see it. Only then is there a chance that you see the problem. Only then do you trigger it, but as I said, the behavior is undefined. So if you overwrite this character, nothing might happen, right? Nothing bad might happen. It might be something that your program doesn't use. It might be a variable that you've set aside, but it's actually not being used, that you're overriding with this. So as you can see, if you would just do random data, then chances are that you have random data that is less than 1,000 characters long. I guess those chances are pretty high. Yeah. So yeah, in order to see this problem, you really have to work with longer source strings, and even then, you're not sure that the test actually shows the problem. The test might trigger the problem, but it might not result in any visible misbehavior of the program. Okay, so that's why this is not really a good solution. These people, the community of the OpenBSD project, they came up with a better solution. I don't have that on the slide, but you can easily open a browser and search for strlcpy. And strlcpy is a replacement for strncpy, where there's just a tiny little change in the semantics of the function. strncpy says the third argument is the number of characters to copy, possibly including the \0 or not. strl-cpy says the target array has this length, and I want a null-terminated string within that length. Yeah? So if I replace this with strl-cpy, then I do not have to put this here, and I can put the 20 here. And then what strl-cpy guarantees me is that I will end up having a C string in message that, including the \0, is no more than 20 characters long. And that tiny change in semantics makes the function much, much, much safer to use, because the programmer just has this little extra, does not have this little extra thing to be concerned with. You know, is the string really non-terminated? This function just guarantees that it is. Okay, some more bad news. You can't really use the double equal symbol. You have a question?
Can we use strl-cpy regularly in C++?
Yeah.
Do we not need an include file or anything?
It should just be done with include C string. What was I going to say? Oh yeah. No comparison using just the double equal symbol for strings. For numbers, yes, of course. For characters also, for booleans. But for C strings, we can't just use the double equal symbol to compare them. Instead, we have to again use a function called strcmp for string compare. And of course, we can pass in two strings. And this is a function that returns a value, and that value that it returns indicates whether the C string that I'm passing as the first argument is less than the second one, whether they are equal, or whether the first one is larger than the second one. And it's well, it returns a negative value, a 0, or a positive value, depending on that. And what it really does is it subtracts the second string character by character from the first one. So imagine you have this, you have in message, goodbye, and you compare it to hello. Well, G minus H is,
That's what we have to use.
well, H comes after G, right? So, and so do they in the ASCII table. So H has the higher ASCII code than G, and so therefore when we subtract them as numbers, these characters, then we get a negative result from subtracting this. And actually here we get a -1 for the first position. Yeah? Because it's G, H, and so on. That already is enough for strcmp. It returns that -1. Yeah? So if the first string comes before the second string in a dictionary ordering, then strcmp will return to us a -1. If they are equal, it will return to us a 0. And if the first one is larger than the second one, then it will return whatever, a positive value. Is that clear? Okay, now what happens? Oh, and it returns as soon as it can. So as soon as there is a difference in one position, it returns that difference. Only returns 0 if the strings are identical, and only then does it have to really go over all of them. So if we have, for example, Jack and Jackie, then what happens? Well, the capital J minus the capital J, that gives us a 0, so we move on to the next position. A minus A, that gives us a 0, we move on to the next position. The C's are identical, the K is identical. And then we have a backslash 0 here, which happens to have the value 0, from which we subtract lowercase y, which happens a value greater than 0. And so we get a minus something, minus whatever. So we get a negative value, and that negative value is returned. Now, if we would have Jack and Jack in both of the strings, then we'd subtract the backslash 0 from the backslash 0, also giving us a 0, but we just saw a backslash 0, which tells us that there's nothing more to look at. And in that case, it returns the 0. Okay, so the way this is used is like this. And now you have to watch out for something, namely that this is going to be non-zero when they are different, right? It's going to be non-zero when they're different. As I just showed you, if the second one is larger, you get a negative value. If the first one is larger, you get a positive value. So you get a non-zero value if they're different, but a non-zero value, if you use it in a condition, means true. Yeah? So you're not really comparing for equality, you're comparing for difference. strcmp returns true if the strings are different, it returns false if they're the same. That's a bit strange, but it comes from the way strcmp is implemented internally. So don't think of strcmp as a replacement for the equal sign. Instead, think of it as a replacement for the not equal. They're different. strcmp tells you, are they different? Okay, yeah, the next one we discussed already. Okay, there are some other string functions. There is strlen, which gives you the length of a string. Obviously, it can be implemented by just starting to count until you reach a backslash 0. You know, you initialize a counter to 0, and then you go on from the starting position of the string, and you just count. And as soon as you reach a backslash 0, you stop counting, and you return the result as the length. It's one way of implementing it. There is strcat, and it doesn't have anything to do with pets. It's the concatenation. It's the concatenation. Everybody knows what that is? It's when you take two strings and you hang one string onto the end of another. That's concatenation. So if I have in message, I just have hello, like this, without the exclamation mark, and then I do an strcit message space and space goodbye. Now what happens is that strcat works almost like strcpy, with the difference that before it starts copying, it looks for the string end symbol here in the target string. So it advances in the target string to the \0, and then it overrides the \0 with the first character of the source string, and then it continues until it reaches the \0 of the source string. And in that way, they're concatenated. And let's see, this gives us 5, 6, 10, 14, 16, 18. Okay, fits. It's your responsibility as a programmer to verify that the current inscription, the current content of the target, plus the whatever you're concatenating onto that, fits into the declared size, including the \0.
Can you put the strcat together with the strl thing?
Yep, exactly. strcat suffers from the same problems that strcpy suffers from, that the programmer has to be concerned with knowing that whatever is in hello together with whatever they have here. I mean, in real life, that's not going to be a constant always, right? That can be just a C-string variable, just like we have here, from which we're copying. Yeah. So it's not so easy to see just from the source code how long it will be, but it's still the responsibility of the programmer to ensure that whatever is in here already and whatever is being concatenated onto it together does not exceed the length of the array, including the \0. So that's exactly the same problem that we had with the strcpy, and there is an strncpat function, but that strncat function has exactly the same problems, if not worse, than the strncpy function. So there, now I answer your question, there is an strlcat function that takes as the third parameter the declared size of the target, and it ensures that within that declared size there will be a null terminated string in the target. Okay, good. Yeah, this slide 19, it illustrates one problem, or it illustrates how strncat even is trickier than strncpy, because strncat also needs as the third parameter the number of characters to copy. But how do you know? Well, for strncpy, you had to know one thing. Namely, you had to know, well, actually two things. You had to know the declared size of the target, and you had to know how many characters you're copying. For strncat, you have to know three things. You have to know the declared size of the target. You have to know how many characters are already in there. And you have to know, well, not have to know, but you use these two numbers to determine how many characters you can copy. Okay, maybe I should back up and take this on from take this on again. So, because I did mix two concepts there. strncpy requires you to know the length of the target. and it requires you to put that extra \0 in the last position of the target. strncat requires you to know the declared size of the target and how many characters are already in there in order to have the number of characters at most that can still be copied on there. And then of course you still have to put that \0 in the last position. Yeah? So there's an additional trap in there, so to speak. Yeah? And, having to know the size, the current size. Okay, now for some good news. After all this bad news, now some good news. The good news is that C strings are arrays. Arrays on which we impose a certain convention, namely that within the declared size there must be this \0. But because they are arrays, we already know how to pass them to functions. Now, passing a C string to a function means passing the array in which the C string is stored to the function. And then of course the function can search, starting at the beginning of the array, can search for the \0 in order to know the length, and so on and so forth. Yeah. Now, if you have a function that writes new data into a C string, then of course you have to approach this like we did with passing arrays before. You have to pass in the declared size in order for that function to be sure not to exceed the declared size. If you have functions that only read from the C string, then there's no, you don't have to pass in the length as an extra argument or anything, because the length can always be obtained by just searching for the \0. And I haven't said this explicitly, but I hope it's clear. Often, knowing the length isn't strictly necessary, because all the functions that you use with C strings, they're just going to process the C string character by character until they run into the \0. So you don't even need to know how long the C string is, for example, in order to output it. A function that outputs a C string doesn't need to determine the length beforehand. It just goes character by character until it runs into the \0. Okay. Another piece of good news is that the insertion operation. Oh, by the way, I was surprised to see how many people got that wrong on midterm number 2, confusing insertion and extraction. By now, I would have hoped everybody got that sorted out. Anyway. I would post the grades today. That's at least that's the plan. You have insertion into cout of C strings. So, for example, this works. And if you have a C string variable, like message that we had just now, then you can also do that. So that works. After all this bad news, this is good news. Yeah. You can also use the extraction operation to get data from a user into a C string. But it's maybe not as intuitively clear how it works as you would expect. So if you have a character array A that you've set aside, and then you do a cin extract into A, and then you type something at the keyboard. Whenever what you type contains a space, that space acts as a delimiter for the extraction operation. So if you tell the user enter input and then the user enters doobie-doo to you, then and you have extraction of two C-string variables, then you get the do into the first and the b into the second, because the spaces between act as delimiters. They chunk up the input. And so this is maybe not exactly what one would expect. For reading an entire line of input, there is a function called getLine to get an entire line, and that is a member function of all the input streams, including your input file streams. So you can get entire lines from your files or from the keyboard from the user by using that function. It has two arguments. C-string, getLine is passed two arguments when you call it. The first one is the C-string that receives the input, and the second one is the declared size. So this is the way you would use getLine. You see it on slide 24. If you run this program and the user enters doobie-doo to you, then you will get the entire doobie-doo to you into the C-string A, and then that takes care of that. That is what you would expect. Oh, there is a mistake on the slide. The leading double quote before end of input is missing. Okay. getLine stops reading when the number of characters -1 has been read, so that -1 of course is left empty for the \0. It also stops when you hit enter. I mean, if you enter a shorter string than the 80 characters in the previous example and you hit enter, then that also stops reading. The enter is not going to be part of the characters in the array. The enter triggers putting the \0, the string end, into the C string, into the array.
What about a file?
Same thing. If you have a new line in the file, then that triggers the end of line.
Is it also undefined if the user enters more than the characters?
No, because how it works, how getLine works, is that it reads up to that number of characters -1, and if the user actually enters that many or more characters, then it still reads only. So if I call it with a second argument 80, then it will read at most 79 characters from you. And after the 79th characters in the position 79, that's the 80th position, it will place the \0. Even if you entered 160 characters.
And what happens to the rest of the characters?
They remain in the input. Okay, so getLine can also be used with files. I mean, that isn't surprising, I hope. The syntax is that you have to use the input object, then .getLine, then a string variable, a C-string variable, and then the maximum number of payload characters that you want to read +1. Or put another way, the declared size of the target. Well, I mean, you don't have to read the declared size of the target. If you have declared A, for example, to have 80 space for 80 characters, and you only want to get 40, that's fine too. You can still call getLine with a smaller number than the intent size. Converting C strings to numbers. We already talked about the fact that all input and all output eventually is done in the form of individual characters. When the user enters 1, 2, 3, 4, that's just a stream of characters, a sequence of characters. And we can read that as a C string, or we can read that as a number. But how are the characters actually converted to a number? That's an interesting question. Huh? What? How are the characters read, the digits, how are these digits actually converted to a number? And well, I'm going to discuss this. It's actually pretty straightforward if you think about it. When the user enters a 1, and we are looking for an integer, okay? So we're looking for an integer, the user enters a 1. That 1 is, in order to illustrate this is a digit 1, that's the key press 1. That key press 1 is a character that has a value if I use it as an integer different than 1. Yeah? Remember I told you about the ASCII table, remember? The character encodings. There is a position and there is a character at that position. And I told you that at position 65, for example, there is the capital A. So when I use a capital A where an integer is required, I'm actually, this is actually used as the number 65.
Exactly, they already have all the letters already have assigned numbers to them.
Right, and same for the digits. The digit 0 happens to occur at position 48 in that table. And at position 49, there's the digit 1, and so on up to 9.
Is there a way to get that mean that then 2 would be 50?
Yeah.
Professor, is there a way to get that same
No. That table is standard. So, but what that means is that I can't just use that digit as a number. I can't just, if my function is supposed to return an integer, and if I would return this, I would be returning the number 49, right? That surely wouldn't be what the user wants. So, what one does in order to convert this is one subtracts the character 0 from it, because the character 0 is at position 48, and so by subtracting these two positions, we get the difference in position, and that's just the value.
So we still give the same result as they were in keys. It would still be 1.
Yeah, that would now be 1. That difference would now be 1. Yeah, because they're just 1 apart. And if I would have whatever 6, then that would give me the integer value 6. So for every digit that I get from the user, this is what I will have to do. And also, I will have to keep track of a variable result that I initialize to 0. And then, so then I have a loop. I keep reading as long as it's digits. Just a second. As long as I get a digit, if it is a digit, so if my input is a digit, then what do I need to do? The fact that this is a digit means that all the digits that I have read up until now need to be shifted by one position to the left, right? Previously I had some digits, say that digits 1 and 1. So I have internally converted them to 11. But now I see another one. That means that what I read up to now wasn't 11, it was 110. Because there's another digit. Yeah? And then I have to get the value of that other digit. I have to add it to this shifted value. Is that clear? Yeah. So if I read 2, 0, 5, so I read the 2, I convert it in the same way to the value 2. I need to, my result is currently 0. I multiply it by 10, that's still 0. And then I add the value 2 into it. So my result is now 2. Yeah? Then I advance to the next item on the input. I see it's a 0. Well, that's a digit. So all the digits I've read up to now need to be shifted by one position to the left, which means multiplying by 10. So I multiply the result I have, the 2, I multiply that by 10, I have 20 now in the result. And I add the value, well, that will give me 0. I add that value, not adding a 0, doesn't change anything. And then I move on to the next position, and I see there's another digit. So that digit gets converted in the same way, and the result I have until now gets shifted by one position, so it's now not 20 but 200. And I add the value that I got here, the 5, to it, and I have 205. Now if we imagine that after that there is a space, then that's no longer a digit, and that process ends and it returns the 205 back to the calling function. That's the way the extraction of integers works internally. And I think I have maybe already gone a little over 10 minutes.